All right, so one more example here, volumes of revolution. This time again with cylindrical shells, except that we will be dealing now with horizontal slices so that we do an integral with respect to y. So we're looking at the region bounded by this parabola, x equal to 1 plus y minus 2 all squared, and then it's bounded with x equal to 2. So the line x equal to 2 is a vertical line. It's going to look something like this. And we have this parabola. Now this parabola has been shifted to the right by 1 unit. Okay, all of our x values have been increased by 1, and then this is going to shift it 2 units up. Okay, so we end up with a parabola that looks like this. And again, this doesn't have to be perfect. If you want to know the intersection of our parabola with the curve x equal to 2, we can solve when is 2 equal to our parabola, and we end up getting that y minus 2 is going to be equal to plus or minus 1, which means we end up with 2 y values as our solutions. We end up with y is equal to 1 or y is equal to 3. And that means we have this intersection point right there when y is 3 and right there when y is 1. So we have our point, x is 2, y is 3, and right here x is 2, y is 1. So this is the region that we are dealing with, bounded between these two curves. And we're going to be rotating that around, in this case, the line y equal to 1. So the line y equal to 1 is going to come in like this. It's actually going to go right through that intersection point, and we're going to be rotating around that line. So we're now going to be looking at doing our slices. Okay, so we have to make a choice. We're either going to be doing a vertical slice or we're going to be doing a horizontal slice. In this case, similar to the other ones that we've gone through, you could do either one. Okay, if you look to do a vertical slice, you're working with respect to x because your thickness would be delta x. But you'll notice right here, the curve is given to you x in terms of y. This one will be easier to do x in terms of y. You don't need to solve for y in terms of x. You don't need to look at these as two different functions. So here, if we look to do a horizontal slice, then what do we end up with? So here, let's take a look at our horizontal slice. Thickness is going to be delta y, and if you rotate that horizontal slice, it's parallel to the axis of rotation. You rotate that around, you will end up with your cylindrical shell. So what we are interested in for our cylindrical shell is what is going to be the radius and what is going to be the height, because we know that the volume is going to be 2 pi, and we're going to do here radius height. We're integrating with respect to y, and we're going to have to get our limits of integration for y. So what is the radius and what is the height? So here, this is what our cylindrical shell is going to look like. And again, you don't need to actually be drawing the three-dimensional shell, but it does help the first few times you go through. So here we have our radius is going to be the distance from the outside of the shell to the axis of rotation. So for us, the radius will be this distance, and our height will be this distance. So going back to our picture, the radius is going to be the distance from the outside of the shell to the axis of rotation. So that's going to be this distance from here to here. That is going to be r, and this distance from here to here, that's going to be h. So putting it all together, if we have this point on the curve, let's suppose that that point has coordinates x, y, then we know the distance from here all the way down to the x-axis is going to be the y value, and we would like to subtract 1 from that. So in this case, you can tell it's just going to be this y value minus 1, And in general, similar to how we did area between two curves, we would always do upper, which is y, minus lower, which is 1. So upper minus lower, we end up here with our radius is going to be y minus 1. And similar to what we said before, one of these two, either the radius or the height, is going to be easy to work with. That's going to be the radius in this one because we have the radius already in terms of y. If I take a look at the height, okay, the height's going to be a little bit more difficult. I want to know what this length from here to here is. So similar again to how we did area between curves, it's going to be the right value minus the left value. So here, the right, what is the x value of this right curve? That's x equal to 2. So it's going to be 2 minus the left value. What is the x coordinate there? Well, it's simply just x. So 2 minus x, again, that's no good. We want to know what is x in terms of y. So that's going to be 2 minus our x value, which is 1 plus y minus 2 all squared. So here, we're going to be subtracting that entire thing. And that will be our height. So now we know the radius, we know the height in terms of y, we can plug it in. Of course, normally we would want to simplify this. I'm going to leave it as is for now. We have our radius is y minus 1. We have our height, which is 2 minus 1 plus y minus 2 squared. Integrate with respect to y. The limits of integration, what is the smallest y value, what is the largest y value? So going over here, the smallest y value is 1, and the largest y value on our region is right here. The largest y value given by that intersection is 3. So we'll leave it like that. This integral from 1 to 3 represents the volume of our solid. And that's it.